On one side, I'm deeply convinced that science has no limits. Yeah, so I mean, there will never be an end to science, as several people postulated in the past. So my most favorite anecdote, maybe you know, this was Kelvin, Lord Kelvin, who declared in the 1900s science is over. We have solved everything. And it was a few years before Max Planck and then Albert Einstein. It was the biggest misjudgment in science history.
Hello everyone and welcome back to the Neuroscience and Beyond podcast. I'm your host Willem, and together with my amazing team of graduate students, we are on a mission to bring the wonders of science, especially neuroscience, closer to you. Today, we have the pleasure of hosting Professor Jörg Enderlein. Professor Enderlein leads a lab at the Third Institute of Physics at Georg August University in Göttingen. His groundbreaking research spans single-molecule spectroscopy and super-resolution microscopy, bridging fundamental principles with biophysical applications. From his roots in East Berlin to his journey through the Soviet Union and the iconic Los Alamos National Laboratory, Professor Enderlein has gained a tremendous amount of experience. His pioneering work has led to the development of remarkable imaging tools that empower biologists like me to tackle complex scientific questions. Join us as we dive into the fascinating interplay of quantum mechanics and microscopy. We explore cutting-edge imaging technologies and uncover captivating stories about the evolution of modern imaging concepts. Before we begin, I'd like to mention that this podcast is a separate activity from my position at the University Medical Center Göttingen in Germany. We are supported by the International Max Planck Research School for Neurosciences, the Cluster of Excellence Multiscale Bioimaging, the European Neuroscience Institute in Göttingen, and the SFB 1286. If you'd like to support us, please subscribe to our channel and leave us a comment below. And now, dear listeners, please enjoy the conversation with Professor Jörg Enderlein. Professor Enderlein, thank you for coming here.
Yeah, thank you for inviting me.
So I was thinking how to start this episode, and to start with a story is always good. And you asked me like a couple of minutes ago, how did you find my profile? Why did you invite me? And I told you this story about how you gave us a lecture like roughly 4 years ago during one of our graduate school lecture series. And it was amazing lecture. I love microscopy. I really enjoy images. I'm a visual person. And the first part about the history, how it developed and why the important milestones was so incredible. And the thing was that the night before, my neighbors, they threw a party and the music was so loud, I could not sleep until, 4 or 5 in the morning. So during the second part of your lecture, I really struggled to be there, and my mind was just gone. Now I would like to hear more about second part of the talk, of course, your work and your opinion on some scientific problems, challenges, and also topics. But can we start? So you have incredible amount of experience in microscopy. You develop very interesting methods and tools. Can we start by mentioning some of the milestones in the development of microscopy in the past, in the history?
Also generally?
Generally, yes.
Yeah, sure. I mean, the whole thing started with my big hero, Anthony van Leeuwenhoek, in the 17th century in the Netherlands. And I mean, it was incredible. I mean, in my lecture, I talked about it. It was incredible that with a single lens system, how much he could see. And he was basically the first pioneer in microimaging. And he could develop. He could see so many things which were completely new. The single-celled organisms, sperm cells, cellular structure in general, bacteria, etc. I mean, it must have been something like a completely new world opening up. It's in the same time, it was also Galilei with the telescope. When he directed the telescope to the heavens, and suddenly he could see the surface of the moon, sunspots, the satellites of Jupiter, and so on, or the galaxy that made of stars. And I think it was an incredibly exciting time to be and to do science. And then, of course, then with Huygens, the next big figure in the play, and Huygens and Halley, Huygens and Hooke, came then the compound microscope. And the funny thing is that then with this two-lens system, basically it remained this way technically until the 20th century. And then only then with the advent of super resolution microscopy, we saw a completely new field opening up. And then nowadays with optical microscopy reaching the nanoscale and competing to some extent even with electron microscopy in resolution.
It's incredible how it developed, and we take things for granted a lot of time, but we need to always keep in mind, oh wow, this actually took several hundreds of years to develop up to this point. I'd like to go back to the 20th century, maybe early 20th century, and talk about one very interesting experiment in physics. You're a physicist by training, so I really like to hear your opinion about that. It's about the functions or the properties of light. That light exhibits properties of a wave and of a particle. And roughly 100-something years ago, or 100 years ago, I don't remember exactly when, this very famous experiment was performed, the double slit experiment, which actually showed that. And can you tell us why is this important in physics, and especially for microscopy, for example?
It's a very interesting story. I mean, when people start to think about the nature of light in modern times, the first modern physicist to do it was Isaac Newton. And of course, he's quite famous. Also, he wrote the first modern physics book about optics. And he was the first guy who came up with the idea that white light is composed of these single colors, and it's a compound structure. And the funny thing is that Isaac Newton, he himself hypothesized that the light is made of particles. And this big opponent was Huygens from the Netherlands. He said, no, this is waves. But at the time of Newton and Huygens, they could not really have an experiment which was decisive. And it took nearly, Newton died in 1724, I think. And only then, roughly 100 years later, Thomas Young in Great Britain, he performed this double slit experiment, which then once and for all people thought at the time was proving that light is made of waves. There's a wave nature. But the funny thing is, the history goes in circles. No? So then in the beginning of the 20th century, was the photo effect, which was difficult to explain. And then Einstein came up with the idea, using ideas from Max Planck, of course, that light is made of particles, of photons. Then the particle nature was back, but of course we also have the wave nature. And then people realized that in reality, light has both properties simultaneously, which is really hard to grasp. Now, how can it be a particle and a wave? In classical optics, what we do, the quantum nature of light per se is not so super important, because you can nicely explain all the optical properties of a microscope by the wave nature of light. It becomes interesting when you consider the interaction of light with single molecules, for example, fluorescent molecules. No? And one of the super resolution methods, so the first one, which was then here invented in Göttingen by Stefan Hell, which is the stat microscopy idea, is explicitly using the quantum nature, using these discrete transitions, electronic transitions in molecules, and then using the properties of excitation and emission of light by these molecules, and that is going on in quanta. So in this respect, then the quantum nature comes back to microscopy, but in a very indirect manner. So, but I mean, when you describe a classical microscope, the funny thing is that the picture has not much changed since the time of Huygens.
But I wanted to talk about something else also, like, in this experiment, they have this kind of double slit where they shoot it with photons or discrete photons, and then they see this pattern around, which then, can kind of conclude, this was a wave here, not a particle coming from one or the other side. And there was this kind of interesting phenomenon that when you record this, when there is some detector, you have one property of light. When you don't have, there is the other property. How is this? Does the detector interfere with the light, or is it something when you write down the information in our reality in this world, then this should be particle or wave? What is the deal there?
Let me tell you a very small one of my favorite stories from history of science. When Einstein came up with his particle hypothesis that light is made of photons, of course it was met in the beginning with a lot of skepticism. So people didn't say, that is how probable is that? And there was one super clever physicist, Taylor, who became later one of the biggest guys in hydrodynamics. And he was a young student when Einstein published this paper, and he said, I have a good idea how to check whether Einstein is right. So what he did, he was building in his home a double-slit experiment, like Thomas Young did, 100 years before. But what he did is he was attenuating the light source so much that he could calculate that if Einstein would be true, only one photon at any time, only one photon would travel through his system. Think about it. You have a light source and you attenuate the light source so much, then by using then Einstein's hypothesis, you know energy and one photon, blah, blah. You can calculate that, okay, I have such an attenuation that on average, only a single photon is at any time in my system. Mm-hmm. And then he said, okay, if Einstein is right and there are photons, then this interference pattern must disappear. Mm-hmm. Because then when only a single photon is flying around, there cannot be any interference between particles. Yeah? Mm-hmm. So only when you have high intensity, okay, many photons, and maybe they interfere somehow. But then you make sure that you only have one particle any time traveling through your system, interference will disappear. So he set up this experiment. And of course, at that time, he only had something like a candle for illumination that was long before any laser or whatever. So it was really, you had to expose this photo film for days. I don't know how long he took. It was an incredible amount of time. So after a very long time of exposure of this photo film, he then developed it. And what he saw was interference pattern. And he said, Einstein was wrong. And the funny thing is that this is exactly the point of this quantum mechanical picture. How can it be that a single photon is self-interfering itself? In my lecture sometimes I show this experiment today with modern equipment. So we have these super sensitive cameras when you can really watch how single photons are hitting the detector, and you see always then a splash of light, mm-hmm. So accumulating. And it is fascinating. I tell you, it's fascinating. You watch these small explosions of light, yeah. And in the beginning it's completely random, and then with time you suddenly see that there is this interference pattern coming up, and it is still, I think, it's one of the biggest mysteries of nature. How can it be? Yeah, I think, and I promise you, nobody, in my personal view, nobody really understands it. Mm-hmm. Even experts in quantum mechanics or quantum field theory or whatever, that is the big mystery. How can it be that you have only single photons and they somehow know where to hit the detector? Yeah, mm-hmm. And when you take out the double slit, then you have a normal pattern as you would expect, yeah, from a photon stream. Mm-hmm. So this is fascinating. Yeah? Unfortunately, in the standard microscopy in biology, it does not play a big role, so we can live without it. But it's really interesting. But I can tell you one experiment. Maybe sorry for long my own talking.
No, it's very nice.
One experiment what we had for many years ago, and was basically then again bringing to our mind that we are talking about quantum mechanics. And this is when you image single molecules. So we are so sensitive nowadays that when we take a normal microscope with a sufficiently sensitive CCD or CMOS camera, we can see the fluorescence emission of single molecules. No? So you can have on your sample very sparse distributions, and then every single molecule will generate a pattern on your camera. Normally, when everything is in focus, then it's simply something like a Gaussian distribution of light. Mm-hmm. So what we by accident at that time, we were not the first to see it. It was people from the W. Murner group in Stanford, but then we repeated these experiments. What we saw by accident is when you defocus your optics, then the image of a single molecule becomes a very peculiar pattern, something like a double banana or a ring-shaped structure and so on. And this is an interference structure. Mm-hmm. But think about when you have only a single molecule, it's completely clear that at any time you only get one photon from your molecule. You excite your molecule, then you have this excited state of a few nanoseconds, and then it is emitting a single photon. So what you see is an interference pattern which is generated by a source which only gives you one photon per time. So this is exactly this quantum double slit experiment, only with a microscope. So the whole microscope is a double slit, so to speak. Mm-hmm. And the photon, the single molecule is your single photon source. And this again is somehow giving me shudder on my back. No? So I mean, thinking about that when I look these images in my camera, I see pure quantum mechanics at work. No?
Mm-hmm. When you say interference pattern, do you talk about the point spread function in this case?
Yeah, so to speak. No? The point spread function for the defocused image. No? I mean, the point spread function is a three-dimensional thing, no? But so you defocus your optics slightly, no? That you are basically an unsharp image, and then you see this interference pattern.
Exactly.
No? So some ring structure or some. It depends also on the orientation of your molecule. It's really very fancy physics. But if you really think deep enough, no? Because you know it's only a single fluorescent molecule. It is a single photon source. No? The molecule can never emit more than a single photon per time, and you still see this interference. So what you see is the interference, the self-interference of these photons with themselves. No? And this is really mystery.
Incredible. And then we as biologists, we have to make sense of our molecules. How to do that, I don't know.
Yeah, but I mean, I promise you. I mean, Feynman, I think it was Feynman who once said this very famous sentence: if you think that you understood the quantum mechanics, you didn't understand anything.
Yeah. I heard some other quote of some other guy in the quantum mechanics. Somebody asked him, do you understand this and that? He said, shut up and calculate, basically. You know, so
yeah, that was his word. Yeah, exactly.
But it's, I mean, as a teenager, I got to watch some documentaries, and I was also captured by all of these experiments. And it's just incredible that we still don't understand. And some of the concepts were formed, as you said, hundreds of years ago. And although we have such a sophisticated equipment, we cannot make sense of all of it. And it's very, very interesting. The good thing is that it's only appearing in this quantum level, so we don't have to deal with these uncertainty principles at our life. You know, we have the Newtonian physics here in charge. So you already mentioned a lot of interesting things about super resolution microscopy and single molecules, and I wanted to ask you, what is the focus of your research?
Okay, good question. I mean, and it's a long story. When I started my career as a physicist, I was doing something completely different. I came from theoretical physics, and then I delved into physical chemistry. And my PhD thesis was about these nonlinear reaction diffusion systems, like Belousov-Jabotinsky reaction, for example, or other reactions also in biochemistry, which are oscillating and out of equilibrium, etc. It was a very hot topic at the time in the 80s, and I really liked it, and it was my PhD thesis. But then when I finished my PhD thesis, that was 1991, then this topic was already more or less basically already, the big things were already done. Yeah, so I was thinking, maybe I should look for some new vistas, some new directions. There was also a Nobel Prize for Prigozhin already at the time for this nonlinear equilibrium, also nonlinear equilibrium thermodynamics. And at that time, by pure chance, I heard about experiments from a guy in the United States, Dick Keller in Los Alamos National Lab, who was the first guy who ever was able to see single molecules, fluorescing molecules in a dense environment like solution, or let's say a cell or tissue, whatever. And I was fascinated by this idea that it is really possible to see and to observe single molecules in real life. Yeah, it was very abstract. No? I mean, Mach already in the beginning of the 9th century, he was attacking the atomic hypothesis with the sentence, "Did you see one?" And suddenly, then 100 years later, we could see them. Yeah, and I was so fascinating that I then by chance I came across a company in Berlin, which was from an East German professor, new founded in 1991. And they were in a consortium together with the University of Heidelberg and other people for developing technology for single molecule spectroscopy. And the main goal at the time was to use single molecule spectroscopy or single molecule detection for DNA sequencing. It was a super hot topic, coming up with cheap and fast sequencing technology. There was this, maybe you don't know it anymore, but at the time there was this millennium thing, $1,000 per genome.
I heard about it.
Big initiative. So everybody was really crazy about it. And then De Keller had this really ingenious idea to use single molecule detection to do single molecule sequencing. Yeah. Also he didn't live up to see it realized. Now there is Specific Biosciences, a big company in California, who is exactly doing this concept in a modified version, but basically the basic idea. So that was the driving force behind. And when they offered me a job in Berlin, I said, okay, that's the new thing. So I completely changed direction and I went into single molecule spectroscopy. And then later I joined also De Keller's lab in Los Alamos. And then that was then the first big thing for me, single molecule spectroscopy. So I'm a spectroscopist, basically. And only when I came to Göttingen, then also, of course, under the influence here, Stefan Hell and all these initiatives and super resolution microscopy, then the idea was from my group, how can we use concepts from spectroscopy to do microscopy? So basically, most of what we are doing is bringing some clever ideas from spectroscopy into the microscopy realm and to do high resolution or super resolution microscopy. This is very short the genesis how we ended up with super resolution microscopy then.
That's crazy. I have to ask you so many questions. I hope I don't forget some. So before I go with this, one clarification, what is the difference between spectroscopy and microscopy?
Spectroscopy, you look really, you typically don't image. Ne? Also you can also combine it with imaging, but per se, spectroscopy means you look at some spectroscopic properties of your emission. For example, emission spectra. Ne? This is the easiest thing to do. Or, for example, fluorescence lifetime. That means you measure the excited state lifetime of your molecules. It is also then very useful for microscopy applications. But it means spectroscopy. You look at spectroscopic properties of light you measure with no imaging. You can, as I said, you can combine it and you have microspectroscopy, but theoretically, the typical spectroscopists, they measure in cuvettes. Simply excite light and then they look what comes back and then they do an analysis. Spectral analysis, temporal analysis, whatever. So this is a big difference.
I just wanted to clarify this for people who have no idea of what these terms mean. Something that is interesting about you, there is this trend of many scientists in Germany. So I've interviewed plenty already and I got to know quite a lot in Göttingen. A lot of them, they go to Western countries to study and they come back here. You went to the eastern side.
I am coming from the east.
You were born in
Berlin.
Yeah. Where, by the way? Which neighborhood?
In Prenzlauer Berg.
Prenzlauer Berg. Yeah. I used to live in Köpenick, by the way, and then in Dahlem-Zehlendorf. I studied at the Freie University. So that's why I was, okay, this is cool. He was in Berlin. Prenzlauer Berg, by the way, is a very nice neighborhood right now. I know about back then. How did it happen, and what is your, let's say, feeling or perspective about? So you were in the Soviet Union, you studied there, and then you went to the US at some point. Can you maybe make some comparison? This could be very interesting for me and for the listeners.
Scientifically,
yeah.
I grew up in East Berlin, and from a very young age, I was really fascinated by science. And then already, I think when I was 13, 14, my dream profession was physics. So it was always the topic which was of most interest to me. And then I wanted to go to the best possible university which was available for me. And of course, there was the Iron Curtain. I could not go to the West, but of course, at that time, Soviet Union was really one of the big countries in physics, and also one of the biggest theoretical physicists there, Landau, Lifshitz, other people. So I wanted to go there. And the funny thing is that there was the chance to apply then to study physics in the Soviet Union. And the funny thing was that the first funny thing was that not many people wanted that. Somehow it was not so popular. I never regret it. It was a good decision. And the second thing is, of course, it was a centralized system. You applied to some black box. I want to study in the Soviet Union. I was hoping for Moscow, but then some administrative guy distributed people by chance. So I ended up in Odessa. And in the beginning, I was not so happy because I thought, I want to go to Moscow, at least St. Petersburg or Leningrad at the time, to the big hubs of physics, Soviet physics, and Odessa was not so super famous for that. But then, and then I applied for moving from Odessa to Moscow, and again, it took a long time for every decision. And then then the decision came after 1 year, and I could have then changed to Moscow. But then I liked Odessa so much that I stayed there. Yeah, it was a good decision. I mean, the physics teachers were really good there, so I had really good teachers. And of course, Odessa is a super beautiful city, and especially today when I see how it is bombed and with rockets by Russian army, that breaks my heart. It's a beautiful city. And then I stayed for 5 years in Odessa, and we had a great time. We were 7 people from East Germany, my physics class, yeah. And I never regretted it. It was fantastic. Then I came back, and then I was again lucky, because I came back in 86 and 89. Then the wall came down. And it was exactly then when I finished my PhD thesis. So I defended 91, and then only a few years later, then I joined the lab of Los Alamos. And again, it was a fantastic experience, because I mean, Los Alamos is basically a completely artificial city. It was founded for building the atomic bomb in 44. But nowadays it's a huge science location and fantastic scientists, and the environment is incredible. There's a national park next by, and so I loved it incredibly. So I had a fantastic time there, and then I came back and continued here in Germany.
Very interesting, very interesting. Yeah, Odessa is not far away from my hometown, Varna, which is in Bulgaria. Yeah. Also the Black Sea. So I've never been to that part of the Black Sea though, but I should visit at some point. Also the other part, I've heard it's very, very beautiful. Yeah, but back to science now. So now you are in Göttingen, and you are developing very, very cool stuff. One of them was developed some years ago, and it's called SOFI.
Yeah.
Can you tell us more about this?
This is the most complicated. I still struggle how to best explain it also in my lectures. Yeah, it is difficult. The point is the following. So I mean, what are the ingredients? What you need is, you have to label your sample. Okay, we are talking about fluorescence microscopy. Yeah, that is the first thing. So you label your sample with something fluorescent. Okay, fluorescent quantum dots, fluorescent molecules, something which is fluorescent. And then the big thing is for SOFI that you need emitters. You need labels which are stochastically blinking. So which are switching between dark and bright, or dark and middle bright and very bright, or whatever. So you need these stochastic intensity fluctuations. And the good thing is that, for example, these quantum crystals, quantum dots, they do it intrinsically. They are blinking on all time scales quite crazy. And then the idea from SOFI comes from spectroscopy again. It comes from a method which is called fluorescence correlation spectroscopy. So what you do is, when you have a very strongly fluctuating signal, you can do a correlation analysis. So what you ask is the following question. You simply ask, okay, if I detect a photon now, what is the chance to detect the next photon a few microseconds or a few milliseconds or a few seconds later? So you measure the intrinsic correlation of your signal. And the funny thing is, when you have two emitters which are statistically independent, and they blink and they simply change their brightness completely randomly, when you cross-correlate, let's say, the photons from the first particle with the photons from the second particle, then this cross-correlation is on average 0. Because when one is dark, then the other may be bright, and when one is bright, the other may be dark. It's completely decoupled. So the cross correlation between these two emitters is 0. Of course, the signal from one and the same emitter is always non-zero, because there is, of course, a very strong correlation of one and the same emitter. So this is the core idea. So what we do is we take a movie. Yeah, we take a long movie of a few hundred or 1,000 images from your sample, and then by pixel, we calculate this correlation. And the funny thing is that all the cross terms, so coming from different emitters, they cancel out. So they're completely canceled out. What you have is basically only the autocorrelation from one and the same emitter. And the funny thing is, because it's the correlation is the second, that's basically what you do is you square the intensity. Yeah, you take the same signal and you square it, because it's a two-photon correlation. So the point spread function of this autocorrelation image is smaller than the point function of the original image. I know it's super hard to explain, especially without any equation or any picture, but that is the core idea. So use intrinsic correlation of your signal to calculate pixel by pixel an image which has a higher spatial resolution. And the funny thing is, by using higher order correlation, which is even more complicated, you can push the resolution basically to whatever you want. I mean, it only depends in the end on the signal, how much signal you have and how much time you have to measure. So typically in practice, we are not going much beyond the fourth order, but at least it gives you something like a 2, 3, 4 times higher resolution. The good thing is that SOFI is extremely tolerant concerning label density or label nature or samples. Basically, you can use the standard procedures of labeling. The only thing what you need is these stochastically blinking emitters. And how they blink doesn't matter. It is extremely robust and easy to implement. The downside is, of course, you can never go to such resolutions like paint, storm, palm, stat, etc. But of course, they are much more demanding than from a technical point of view.
So you do it with a normal wide field or confocal?
It's normal wide field camera. The funny thing is also that this might only as a side remark that SOFI, or even the lowest order, gives you already optical sectioning, so which is also super not easy to explain. The normal wide field microscope, you don't have any depth resolution. So if you would take a Z-stack with a normal wide field microscope, you see only quark. But I mean, when you do the SOFI trick, then you, with this wide field imaging modality, you have optical sectioning. It's really funny. Suddenly you see the 3D coming out from your SOFI images, and this is also one of the properties we are using then for our imaging modalities.
It's very cool because it gives opportunity to labs that cannot afford instruments worth millions of euros to perform nice experiments on a deeper level, right?
Yeah, this is one of the. I mean, of course, you need a sensitive camera. That is still required, but otherwise, it's a standard wide field microscope. And one of the advantages I would say is also that it has several advantages. That it also suppresses background, because all background which is not fluctuating is simply cancelled. It gives you a 3D thing, and gives you some higher resolution, and you can also be much faster than, let's say, with the standard single molecule localization microscopy, because you don't have to localize single emitters. You can simply take this movie, and in one shot you process the movie and you have your high resolution image. So you can theoretically go much faster.
So it's
for live cell imaging, for example.
That's true, because indeed the other that you mentioned, the Storm and Palm, these are the other sophisticated single molecule localization microscopy methods. They require this hours of imaging of your.
I mean, there are
matters.
people on the planet, like for example Jörg August from Yale University, who are really pushed the limits to going faster with Storm, and it's really amazing what he can do. But it is really extremely challenging. To have something like a few second efficient frame rate.
And it's also not suitable for live imaging, I think.
As I said, Jörg does it, but it is really at the edge what you can do with the method. Normally we use fixed samples for paint Storm.
It's probably not like that easy, as you say. And I mean, it is indeed challenging. And now there are these surf things that are also kind of based on SOFI principle, right?
Yeah, it's on the same idea basically. What they do a lot of more convolution steps in between.
There is something similar,
which can be dangerous. So this is a problem. I mean, SOFI, the good thing is, from a physics point of view, SOFI has a completely clear pattern how the final image looks like. I can write down on paper how the point function looks like for SOFI and order. With SIRF, this is impossible, because you have so many adjustable parameters, and you have to do some thresholding and convolution steps. So that is really an open question, by the way. I mean, how much artifacts, or how artifact prone is SIRF? So let's see. But it is still under research.
The field will show it in a couple of years from now. Very interesting. By the way, what does SOFI stand for?
This is either super resolution or stochastic optical fluctuation imaging.
Yeah, I just wanted to clarify, because we talk SOFI. Who is SOFI? SOFI is not here. Very cool name. And recently, you had an article published in one of the respective journals about a new method, how you basically fine-tuning, if I'm not mistaken, the detectors. You can have a very, very nice resolution also in the axial domain.
Yeah.
Can you tell us more about it? It's also very complicated, but we can try.
I think it's easier in SOFI, at least for my taste. The idea is quite fun. This is then now going back to the quantum nature of light. So let's simply focus on the fluorescence emission of a single molecule. Yeah? So you have a molecule which is nicely fluorescent. So what you can do, you can excite it with a laser pulse into electronic excited state, and then it remains there for a few nanoseconds, which is for us super short. On a molecular scale, it's super long. Typical processes are typically femtoseconds, attoseconds, so that something is remaining for nanoseconds in one excited state is a long time from a molecular point of view. And then after these few nanoseconds, it jumps back, and then typically, if it's it's a nicely fluorescent molecule, it emits a photon, and you can repeat the cycle over and over and over again, and then you see a lot of light from your molecule. And then when you have many molecules in your sample, then you get an image. The funny thing is that when you take your single molecule, and you bring it close to a metal film or some metal surface, you start to modulate the excited state lifetime. Why? Because, what is light? Light is an electromagnetic wave. And what is a metal? A metal is nothing else than basically it's a reservoir of free electrons. So when you have free electrons and they feel an electric field impinging on them, then they are starting to oscillate, and they can grab the energy, they can absorb the energy. That's why metals are opaque. So when you shine light on a metal, then of course all the light is absorbed. This is exactly by the free electrons in the metal. Only a part is reflected. So what is happening when you take your single molecule and you come close to the metal, then the emission of your molecule can excite oscillations in the metal, electron oscillations, and this makes then the return of your molecule to ground state faster. So the closer your molecule is to the surface, to the metal surface, the faster it returns to the ground state, the faster it emits light. So what we then developed was the following idea, and this is old physics, not from us. It was already very well known in the 1970s, last century. Fantastic papers. There was one really big physicist here in Germany, Drexage, who died a few years ago, who was done doing these groundbreaking experiments. So it was already well known. But our idea was then, okay, the physics is super well known. What about measuring the excited state lifetime of a molecule? So we can measure nowadays relatively easy how long your molecule on average is remaining in the excited state before it emits a fluorescence photon. So we measure that, and then we have a metal surface somewhere, and then by using this time information, so about this excited state lifetime, we can then back calculate the distance of the molecule from the surface. That was the main idea, because there is a very one-to-one relationship between the excited state lifetime and how close your molecule is to the metal surface. The closer it is to the metal, the faster it comes back to the ground state. So this is this relationship. Unfortunately, it's only about something like 200 nanometers. In this range, you can do the trick. When the molecule is too far away, then the metal doesn't play any role anymore. So there's this kind of interaction range. But within these 200 nanometers, you can use this effect for measuring the time information, and then convert it into a distance. And it was a very crazy idea in the beginning, and then we did it, and it worked instantly, amazingly well. So we could localize as a single emitters with nanometer accuracy above the surface. And this then we called metal-induced energy transfer imaging, because it's a metal-induced energy transfer from the molecule to the metal. This is very similar to FRET, first resonance energy transfer, where you have a donor and acceptor. And also there you use this donor-acceptor energy transfer efficiency for measuring the distance between the two molecules. So we do the same thing, but the acceptor is the metal in our case. So the experiment in the end is quite simple. We take a normal cover slide, and we cover it with a very thin film of metal, typically gold. So thin means 10, 20 nanometers. It's transparent. You can look through it. And on top of that, we do the standard microscopy. You take some cells or tissues, whatever you want to measure. And then the only prerequisite what you need is a fluorescence lifetime imaging microscope. You need a microscope which can not only measure intensity images, but also the lifetime. And then we convert this lifetime information into a distance. And it gives us then a topography of whatever you look at with extremely high X-ray resolution. And this worked also amazingly well. And we have used it now in many, many different contexts in biology, focal adhesion complexes, nuclear pore organization, whatever. So this is the idea.
That's very cool, and this would work for my project actually quite well, for
invited.
Extracellular matrix, because it's also on the surface quite a lot, on the cover glass deposited there, So the only thing besides the film modality of your microscopy, you would need gold-covered cover slips. Okay.
Yeah, but we make them ourselves in our lab. It is relatively easy. By chemical vapor deposition, you can simply cover standard cover slides with this very thin gold film. So this is the standard procedure.
Oh, that's cool. How do you get inspiration about all of these, things? Is it like you talk to biologists or you read?
Sure. This is a big input. So I mean, looking what people need. Also in my case, I would say conferences. Really. Also. That is all my coworkers, they fear when I go to a conference because I'm coming back with 90 crazy ideas, and 89 don't work, but one maybe, But for me, going to conferences, talking with people, seeing what other people do, that was extremely inspirational always, and that's really the case. I'm going to, I think all these SOFI, whatever, that somehow it came from conferences.
But conference in physics or not?
No. I mean, for example, microscopy conferences. There is this fantastic focus on microscopy conference every year, or there is the methods and applications fluorescence spectroscopy also every year. So there are these big or Biophysics Society meetings or DPG meetings, whatever. So and I think if I think back, I would say most of this inspirations came something from these interactions, speaking with people, watching what other people do, also thinking what other people need, and So this is, for me, it was always super important. I never could come up with some crazy stuff simply sitting in my corner in my lab.
This is no way. I mean, unless you, read only papers the whole day, and this is even...
Yeah, some people can do that, but I need this human interaction.
Exactly. And then you have in your team mostly physicists who develop the things?
No. I mean, this is really nice. We are totally mixed. We have biochemists, biologists, we have chemical physics engineers, everything. One of my best students now, for example, is what is he exactly? A biomedical chemist. So he's a medical doctor. He did medical. He decided medicine with biochemistry somehow emphasis, and now he is doing programming. He is amazing.
Completely talented person. I wanted to ask you the following. So, in terms of resolution or our ability to distinguish two dots as separate in our images as they're separate in the sample. We've pushed the field, I mean you guys and also other scientists enormously, and then there's, as you mentioned, this single molecule localization microscopy, PalmStorm, STET. Now expansion microscopy is also kicking in, another modality. Your new methods that you're developing, basically we're going into almost below the nanometer resolution, which is electron microscopy domain. It's incredible. First question is, where is the limit? and the second question, so maybe even three questions I wanted. First, where is the limit? Second, do we need this information? And third is, are you aware of, probably there are people who are working not in the domain of resolution, but of the speed of acquisition? Because I am definitely sure that if we are able to capture events that are on these like femto picoseconds, then we can really see also a totally new world.
Good question. I mean, where's the limit? Let me first answer, where's the limit? I mean, I would say we have now reached the limit. So now we are talking about angstrom resolution fluorescence microscopy. So there's here Stefan Hell with his MinFlux method, or there's, of course, Ralf Jungmann in Munich with pushing paint to unheard limits, yeah. And I would say now we are limited by the labeling. No? I mean, because the molecule has a finite size, you need a linker to link it to some structure of interest, and this is now much bigger than the resolution you can achieve. So I would say that we are now at the end with resolution. Speed, yeah, that is the big problem. There's something like a Heisenberg uncertainty relation between speed and resolution. For getting high resolution, you need light. So that is, for example, in single molecule localization, very roughly, rule of thumb, the resolution goes down like the square root of the number of photons you collect. So when you want to have angstrom, and you start with something like 200 nanometer, then you can calculate you need something like 100,000 photons. So this takes time. So you need this time to collect this much photons. So that you cannot go much faster then. And I would say, that is the big thing we are all struggling with. And when you want to go fast, then you have to sacrifice some resolution. If you want to have nanometer resolution, you have to sacrifice speed. And that's why I think that is also a good thing, because that means that no single method is the everything method. So I mean, for example, we talked about SOFI. SOFI will never reach the resolution of single molecule localization, but SOFI can be fast. When you go single molecule localization with paint angstrom, this is nice, but you will never be fast with this method, and so on. So it really depends what you need, what is the resolution you want to achieve, how fast you want to go. Then we also have this one method for here, structural illumination microscopy, or our Airyscan, also what came from our lab. Again, resolution is limited to 2 times the original resolution, but you can be super fast, and you can multicolor and whatever. So that is really the question, what you need for your specific application. But to dream about something like a live cell nanometer resolution with 50 frames per second, no, I don't see that.
I mean, there are some commercially available I don't know, how do you call them, like software enhancements. One of the big companies, Leica, they have some, I haven't tested it, the tau extent, where they claim that you can do STET with very, very, very little laser power, and then they have some computational processing going on, which gives you nice resolution, and it's also like not harmful for the sample. But this is, I haven't tried it, I don't know, I cannot tell anything. But as you mentioned, probably it's a matter of trade-off. What do you need? And you cannot have it all at one time. I just want to say something. You said Airyscan comes from your lab, or?
Okay, the story is the following.
That's very interesting. I don't know.
I mean, this is maybe not exactly correct. I mean, the idea, the core idea of this whole technique was developed already in the 1980s by an ingenious microscopist, Colin Shepard, who is one of the towering figures in microscopy. And he wrote a 2-page paper in 1986, I think, about this core concept, how to double the resolution of a confocal microscope by combining it with an imaging detector. But then the funny thing is, nobody ever took this idea up. It was a theoretical paper, 2 pages. Nobody ever took this idea up and realized it. And only in 2010, by chance, we came to the same idea, not knowing about Colin's work. And then we published the first experimental realization of this idea in the Physical Review Letters, in a very physics-oriented journal. And then 1 week later, after our publication, Carl Zeiss called me and invited us to Jena and said, "Oh, yeah, interesting, please give a talk in Jena." So we went to Jena, then my postdoc and me, and Bernd Müller, and then we presented our ideas there. And then it occurred that they came to a very similar idea independently. And they were already working on this commercial product, which then became later the Airyscan. So obviously this idea was somehow in the air. It was only by big luck that we were the first to publish it. And then I think they invited us because they wanted to check out whether we have a patent. That was their main concern. Oh, wow, the enemy. So when they learned that there is no patent, then they were quite happy. But that didn't help them so much, because they didn't also not know about Colin Shepard's paper. So only later, then a colleague from Delft told me, "Oh, Jörg, there is this one theoretical paper from 30 years ago from Colin who is describing, and even the equations are identical." Wow. It was amazing. And then, and then of course it was also ruining then the size pattern to some extent. Yeah. So that was the development. So I cannot claim that they took our idea, but that was simultaneously, independently. But by luck we were the first to publish it, and then of course I was super happy. Somehow, it was simply satisfying that then science then now is marketing as the Airyscan. So if you see an idea you had then the flourishing, it's always nice. No?
It's very interesting. They have this microscope from the company Zeiss, obviously, that they don't have pinhole, right? This Airyscan that doesn't have pinhole. It's just
don't need
an array of detectors.
Exactly. This is the idea. No? You don't, because basically in such an instrument, the pixel of the detector, each pixel is basically the pinhole. Yeah. So you choose the magnification so big that every pixel is acting as the pinhole of your detection system. Yeah.
That's so crazy. When I listen to this kind of stories, I'm thinking about, okay, are ideas born or they're just discovered? So somebody had this, and then it's so interesting that somebody 30 years ago had very similar, and then suddenly, it's incredible.
Yeah. And the funny thing is that was really surprising to us that, this is an ingenious idea. And I tell you, I'm completely convinced that within a few years, every confocal microscope will basically have this option in there, because it is so super easy to realize. And now we also see a small revolution in detectors. There are now these since a few years, these so-called spot array detectors. They are pixelated small detectors of only a few pixels, but using single photon avalanche dyes as the detection, and they are super fast and super sensitive, and the prices are falling like crazy for these detectors, because now there are several companies who make them, and that means to convert any confocal into such a high resolution system is super simple. So I would claim that no company in the long term can avoid to incorporate this into the system, because for competition purposes they have to do that. This idea was, as I said, published in the 80s by Colin, and it was never taken up at that time. And instead, people then started to develop a comparative idea that was the structural illumination microscopy. That was Gustafsson from the United States, which then became a big thing and then commercialized in many companies, which is so much more complicated, technically than this Airyscan idea, which is amazing. So people somehow went into a completely different path, and only now they come back to the simpler solution.
It's incredible. I took part in a remarkable course on microscopy at Cold Spring Harbor Lab, and they have there one of these very first sim, which is basically one big room with a microscope. Then there was another, it was a microscope body with 4 cameras with no ocular, and you had another microscope that you have to use to find your samples, and another, I don't know, a wardrobe full of some kind of other tech, I don't know. It was so crazy to see.
They were auch incredibly expensive, these systems. I think it's the OMX microscope.
Exactly this one.
The hellish machine. They were good. They were really good, but they were incredibly expensive and technically challenging.
It was fun to see when you press this thing, open the box, and you see the fringes are moving. Cool. Why do you think some people? Why do you think these ideas, that this particular one, 2-page paper, it was not picked up by the community?
Good question. I think at that time, the detectors were not ready yet. So for realizing this Airyscan idea, you need an imaging detector, at least a few pixels, but an imaging detector which is fast. Fast means really that you can take a signal with mega counts per second. So mega frames per second. And at that time, when Colin published this paper, this was simply not existing at that time. So what Zeiss did, it was a very clever idea. So they had, as a commercial product, they had a confocal microscope for spectrally resolved confocal imaging. So what they did is they had their confocal microscope, and let's say 4 laser lines for excitation, and then when the fluorescence light came back, they split it by a diffracting element like a prism or a grating plating into the different colors, and then they image these colors onto a PMT line array. Yeah. So basically, they had this multi-pixel detector already in there, but for a completely different purpose. Yeah, for multicolor imaging. And when they hit on this Airyscan idea, with one shot, what they did is the following: they took a fiber bundle, a glass fiber bundle. So and on one end it was an hexagonal array of fibers. Yeah, that was the entry, and they imaged then the fluorescent light on this hexagonal array of fibers, and then they distributed the fibers onto the linear PMT array, which they already had for spectral imaging. That was the idea. Yeah. And the PMT array is a super fast detector, so you can take basically images with mega frames per second. And that was all what they did. So they appropriated the technology which was already there for a completely different new purpose. Yeah. When we published our first paper, we used the standard EMCCD for recording. It worked very nicely, but it was ultra slow because we had to take an image, and the camera could only take 100 images per second. So our scanning was ultra slow. So when we showed it to our biology guys here in Göttingen, they were running out of the lab, laughing. Nice idea, but what is the use when you take an image which takes an hour? So only now with these fast detectors, especially the spot arrays I was mentioning, I think we will see now a revolution in the field, because now it really becomes absolutely feasible for everybody.
But what are these spot arrays? So what is the difference? I mean, if we can maybe distinguish between the camera and these guys. Let's say CCD camera.
A single photon avalanche diode. This is a silicon point detector which is detecting single photons. An idea is when a photon hits the detector, then the electric signal is generated, and then you record this as an electric pulse. And then the next photon comes, you see again a pulse. So we use it normally for doing lifetime measurements in spectroscopy. So far, so good. But what now these companies, since something like 3-4 years, what they have done, there's one company in Switzerland, another company in Italy, different people. What they have come up with now to have some small arrays of these spots so that you can take images. So we are using now spot arrays. They have only something like 23 pixels. But this is completely enough for taking a super small image of the confocal region of your confocal microscope. This is all what you need for this kind of Airyscan idea. And these spots, they can take signal with extreme high count rates. So you can basically take images with mega frames per second. So that means you can really scan very fast, as you do in normal confocal scanning. Resonance scanning, you take very fast images. And the imaging detector is so fast that it can, with this speed, take images. And this is what you need. And this was not there a few years ago.
Wow. Let's see how long it will take for the companies to commercialize it, and then.
I mean, this battery is now
already. You
it's
said
commercially available. It's I think they sell like crazy, and you see it also in the literature. When you look in the literature, that we can really follow it in real time, how papers are exploding using these detectors. I think that is the future, the future of confocal microscopy. So to say.
Of laser scanning confocal.
Laser scanning confocal.
Spinning with different. Interesting. I've never heard. I mean, I saw these things in the paper that you published, the spot arrays, but I've never heard of them, which is cool. So basically, the speed is very, very, very high. That's suitable for live imaging. Let's see. Maybe we have to talk to Silvio about some new things.
Silvio knows about it. He's the co-author of one of the papers.
No. I know. But we recently acquired some new machine that is very expensive. So I don't think that we will have a new fancy microscope soon. So who knows? Maybe the other PhD students and postdocs will benefit. Are there any exciting? So you finish now. Let's say you wrap up this story with the one. I don't know. We didn't coin the name. The one that combines the film with the metal detector.
This was metal-induced energy transfer.
Metal-induced energy transfer. Exactly. What kind of other projects are you working on right now?
Good question. Also at the moment we are again shifting slightly back to spectroscopy. We think we have a cool optically spectroscopic method to measure electric charges of molecules in solution. And I think this is maybe it will not work out. It's very speculative. But it would be something I would really like to explore in the near future. Because, electric charges are super important when you go to biophysics and biology. The problem is that it is super difficult to determine. We all know, my protein, there are charges. We even know that electrostatic charge distributions in proteins and enzymes are involved in enzymatic reactions and whatnot. Or interactions between molecules. Take a DNA, highly electrically charged, and that plays a big role in DNA, also in hybridization, whatnot. So, electric charges are everywhere, but nobody really can measure them easily. Yeah, so not at least not on a single molecule level. So I think we have a clever idea, maybe, how to do it. For biomolecules, for enzymes, for proteins, for RNA, DNA, whatever you take, and this would offer a completely new field for doing biophysics. For example, only one crazy idea. Take an enzyme. And it is completely sure when an enzyme binds the adduct for reaction and then the product is formed, then this comes along with electric charge changes of the whole complex. So when the ligand is binding to the enzyme, there will be a charge change because the electrostatic interaction between ligand and enzyme is super important. So think about, you can measure electric charges of single enzymes, and then you could watch enzymatic action on a single molecule level with simply by monitoring the charge changes, or charge fluctuations. So this is some idea we are now pondering. This is still a long way to go, but maybe this is the next thing in our lab. Let's see.
Well, that's very cool. Then this detection should be super fast also, right?
Yeah, sure. But we are, as I said, we are coming from single molecule spectroscopy. So I would say we are the experts for super fast and super sensitive measurements of single molecules. So that's why I say, maybe we are moving back again to more spectroscopic stuff. With the idea, addressing something like electrostatic charges in biomolecules.
And you said in solution. Does this also mean in vivo when they happen, or in?
This is mostly at the stage now in vitro, but under physiological conditions for sure.
That would be interesting indeed. Wow. I've never heard about anything else that measured this in vivo, but of course, who am I?
In vivo, in vivo it will be.
Sorry, in vivo I mean in cultures, let's say, in the real environment, not like in the animal or.
The problem is, when you take a cell, it's full of proteins and stuff, and then everything is electrically charged.
Exactly.
So this would be the problem, the specificity. So how can you measure? That you say, protein X, protein Y, protein Z. That is not so easy.
What if you couple your measurement with another feature, like some, again, tagging of the protein, so that hey, this is what I'm measuring.
That would be an idea then to have some intermediate optical labeling and then somehow reading it out. But we are at the very beginning.
We're just speculating.
And I would be already happy if I could, let's say, watch single enzymes in vitro. That would be already one of my big dreams.
The biochemist community will be very, very happy for sure.
There had been spectacular measurements of single enzyme activity by optical methods many years ago by Zhani Ji from at the time in Harvard. But the problem was that it was restricted to enzymes which are somehow producing a fluorescent product. But the results were spectacular. He could show that enzymes can have memory and non-trivial kinetics and so on. That was a really big splash. But then, but that was then the end of the story, because the 99% of other enzymatic reactions are not accessible to this method because you need an optical readout. So we hope with this electric charge measurements that maybe we can then really extend it to all enzymes. And I would say that would open completely new field.
Indeed, that's incredible. I wish you a lot of success with this project, and ideas. I'd like to ask you some one or two questions in the remaining time that are also scientifically related, but not particularly to your topic or some technology or something experimental wise. So let's speculate a bit. I have a dream to create some kind of an institute that combines research institute, university, and biotech company in the future, And I'm asking people who are coming to our podcast to share their idea of the following. You have a lot of experience, I'd like to ask you, imagine you have unlimited resources, financial resources, to lead an institute in the next 10, 15, 20 years. How would this institute look like?
I can give you two examples which are existing on this planet. Yeah, one is the Weizmann Institute in Rehovot in Israel, and then there's this ISTA, the Institute of Science and Technology in Austria, next to Vienna, which is modeled after the Weizmann Institute. And these two institutions, to my experience, they are the most successful institutions in this respect. Having small, also for example, one idea from the ISTA, also from Weizmann, you cannot, when you get your group there, you cannot get beyond something like 15 co-workers. It's forbidden. I like that. It is prohibiting these mega empires of something. You have to be small but powerful. And I think this is one of the things. Then, of course, the second thing, what both institutions have, in high diversity. So they have from fundamental physics to super applied biomedical stuff. So this is also the big strength, this extreme interdisciplinary character of these institutions and the chance that people can interact with each other. And I did my sabbatical in Weizmann a few years ago, and I didn't do much science because I was only running from one talk to the next talk, from one meeting to it was so exciting. I learned so many things in this half year. It was incredible. This inspiration you get from this kind of interaction is incredible, and this is something I partially miss maybe here. But but I think these are institutions. I would say if you want to found a new institute, go there and learn how to do it.
Good point. Why do you want like 15 people or a limited amount of people?
I didn't do the research. One would have to do some deep research. But I'm pretty sure if you measure output per money, you will see there is a maximum, and then when you have 100 people in a group, efficiency goes down. Sure, they have their 2-3 science papers per year, but the effort and the material and the personnel what they use for that is incredible. So I don't believe in these big empires. I know some scientists, it is their big dream to have the bigger the better. I don't think it's very efficient.
Yeah, and also for you as let's say, you are a mentor to some of the students. This is also becomes.
I can tell you from my experience. I mean, when in my highest time, so to speak, I had something then more than 20 co-worker students and other PhD students, postdocs, and so on. It was too much. I could not spend enough time anymore for interacting with everybody as I wanted. It was frustrating because all the time I had the feeling I'm not enough there for my people. And I never want to have this again. So I think 10, 12, maybe 15, that is the maximum you can manage, and you can still contribute reasonably well. Beyond that, you become an administrator, but not scientist anymore.
It's mostly like writing grants and whatever. I don't know, dealing with problems at our lovely institutions here and there.
I mean, some people love it. So some people really do it on purpose, and they don't do any science anymore, but they really do this administration thing and representation thing, and they like to be invited everywhere and blah blah. But it is not my dream.
That's true. Everybody is different, and we respect everybody's opinion and desires. That's very interesting. I never heard of this restriction of the personnel. I heard of this institutes, of course, Weizmann and ISTA in Austria. Actually, one of my colleagues from the master program, Daphne, she we started this idea with her back then, but she moved to ISTA afterwards. Yeah, so probably we will meet soon somewhere. We have to catch up. I know that she loves it, and it's a very nicely organized institute. And you have there also people that make for you things in terms of genetics or whatever. It's really basically people wanted to create environment for scientists to thrive. That's it. There is nothing less or more than that.
Exactly.
Yeah. And it's also in a very, very, very lovely city. Vienna is, I was there recently. I'm really impressed.
Naja, okay. Also Easter is in Neuburg.
Yes.
Quite far outside.
Yeah. But still, it's, you can live in Vienna and work there. It's not a problem. But yeah, still a very, very nice location. The other question that I'd like to ask you and maybe close our first part of the podcast is actually a quote. I wrote it down here from one of the very, very, very famous physicists, Max Planck, right? I will read it now. So, science cannot solve the ultimate mystery of nature because in the last analysis, we ourselves are a part of the mystery that we are trying to solve. This is Max Planck, right? So, what do you think about this? Are we going to understand the true nature of reality at some point in our life as a physicist and as a person?
You know, I'm probably the wrong person to ask. Yeah, this goes very deep. I would say yes and no. Yeah, I mean, on one side, I'm deeply convinced that science has no limits. Yeah, so I mean, there will never be an end to science, as several people postulated in the past. So my most favorite anecdote, maybe you know, this was Lord Kelvin, who declared in the 1900s science is over. We have solved everything. And it was a few years before Max Planck and then Albert Einstein. It was the biggest misjudgment in science history. Yeah, but on the other side, I mean, I think it's indeed, I mean, the new biology, new physics, also understanding brain, understanding conscience, it's the question of how far can we go, because we are investigating ourselves. I don't know, but I would say in the end, the good thing is the adventure will never end.
That is true.
But you see it now with artificial intelligence. I mean, everybody talks about it, nobody understands it.
It takes time. Maybe we will get it. I don't know. Maybe we don't need to understand it. As long as it's there and helpful, who cares how it works?
I don't know.
No. Joking aside, but Let's see. This was one of the reasons, by the way, why I tried to become a scientist. There will be work for me for the whole life, even many, many lives ahead. It's just very incredible that there are so many things that we don't understand, we don't know, as you said, and I think we are never going to be able to answer everything in one or even many, many lifetimes. So there will be always something to keep you busy, and it's not going to be boring at all. Professor Enderlein, thank you very much for coming to our podcast.
Thank you.